Okay, so thank you all for being here. Coming to you live from the illustrious basement lab, where I've been for the last 7 months. So I'm going for the most uncultivated Zoom backdrop of the conference. So today we're going to give a little bit of less of a technical talk about how the system works and more of a sort of like design talk about what is the tool like, why is it like this, and why do we need something like this. So to do that, I'm going to tell a little bit of a story. And this is a story of how would we go about studying a behavior like this. We observe that mice bob their heads to judge a distance before making a jump. And so pretty straightforward behavior. What kind of tools would a neuroscientist need to study this? So one, straightforward, let's just study it open loop. We're just getting off the ground. We're just getting invested in this project. So we're just going to hook up 2 high-speed cameras, write some simple script for it that captures the images. And then later on, we're going to do some deep lab cut analysis just to like sort of quantify the behavior. First of all, simple enough. 2 components, 1 computer, great. Next thing we want to do is be able to control the platform that the mouse is jumping onto. So we go over to the machine shop, ask them to build something that's a motorized platform, and they come back to us with something with this beautiful behavior, but a very esoteric and complicated way of controlling it. So we need to write some custom firmware, but our computer doesn't have a serial port, so we need to use a little microcontroller anyway. And so we have to write some firmware for it in C and then write some special serial protocol to communicate with that microcontroller. So okay, the complexity not too bad, 2 computers and 1 controller, but we're not quite at where we want to be at. Where we want to be, closing the loop. So in order to close the loop, we have this motorized platform. We're studying this bobbing behavior. So we want the platform to counteract the bob of the mouse. And so in order to do that, we have to get the motion data from the mouse really quickly. So we need to gather data from a motion sensor that we've implanted on the mouse. We also, while we're at it, want to gather video from the mouse's point of view and some pupillometry while we're at it. Neuroscientists, we just need to maximize the data streams. So, but our first computer is already maxed out. We have 2 high-speed cameras going on it. We're controlling another microcontroller, and just the computer is too sluggish to handle 2 more video streams and another motion sensor. So let's get another computer in here. So the second computer, but the problem is the second computer, we haven't thought about how to do the synchronization. So we come up with what neuroscientists usually do, is make some sort of synchronizing TTL pulse that flashes an LED in our camera so that we can see when that is happening in our video, so that we can synchronize it later. Unfortunately, that doesn't let us do real-time image processing as easily as we'd like to, because it needs to be aligned after the fact. So we had to compromise on some of our experiments. But at this point, we have a working closed loop experiment. And I'm going to skip a lot of the details here. And so on it goes, where we also want to gather electrophysiological data. We also want to control another set of solenoids to deliver rewards, etc. So the complexity only compounds when we get into the full experiment. And what about the data that comes from an experiment like this? So we have, 10 or so different types of data. They've been gathered at different times in the experiment as we developed it. They're all on different computers. They might be in different formats. We need to write code to synchronize our video that's been taken. God knows what the organization is like, if there is any metadata at all, and whether we've preserved information about the animal's training history as they've been going through the different iterations of the task, all up to question. So basically need to write another library just to clean the data. And then we haven't even talked about the entire infrastructure for writing the task in the first place. So is this some script that we wrote from scratch? If we were using some prepackaged behavioral library, how does that integrate with the rest of the tools? We have multiple computers. Are we walking around the lab to start all these scripts at the same time? Or if we're very fancy, we have some bash script that starts it all for us. And that also ignores sort of any training or shaping that needs to go into it. The mice don't just jump up on the platforms themselves. We have to sort of train and shape this. So did we just write multiple scripts? So I think that using this as an example, thinking about what the next 10 years of neuroscience experiments are going to be like, where this is just one example of a way that a neuroscientist would typically tackle a project that they want to do. But I think it's indicative of the larger structure of these type of experiments. So lots of hardware, lots of heterogeneous hardware that just like doesn't know necessarily how to talk to each other. we're a mix of custom and off-the-shelf components where we don't want to do everything from scratch. We want to be able to buy cameras, for example, but also we're going to have whatever weird stuff we have lying around the lab, and we need to be able to accommodate both. We need to have all-to-all control. So that's the nature of closed loop and real-time behavior. You need to be able to take some input data stream, really easily plug it into some output and be able to control that. You need to do the real-time data processing to make that possible. So taking image, processing the image, converting that to some useful information. And synchronization, of course, needs to be baked into the core of the library. The tasks it needs to do need to accommodate sort of like more complex process through a task. So train the animal, shape the animal. And then when we get into the high density silicon probe recordings we all know and love, and the wide scale calcium imaging, we need to be able to accommodate high bandwidth and multimodal data collection. So what does that mean for the tools that we need? We need them to be flexible. So first of all, we need to be able to use any hardware that we have and write any task that we need. So what we need is a framework rather than a program. We need something that we have a set of tools that we can build experiments with rather than something that's sort of limited off the shelf intended to do X things. So we just need to separate the tools from their implementation as a software. They need to be distributed, and there really is no getting away from this. At the point when we need this many hardware components at a time, you have to use multiple computers. And if you ignore that component and sort of treat it as an afterthought, you're going to be doing a lot of cleanup later. So it just should be distributed from the start. And I'm glad to hear that we're talking about reproducibility in this panel, because that's the other thing that we need to fight. We have these better angels within us that we want to do good science, but we also have this beautiful instinct to just hack stuff together and make the one idiosyncratic rig in the world that can do this experiment, because only I know this one pattern of resistors that seems to work sometimes. And so we need to have data that's clean, complete, and annotated at the time of acquisition to lower the barriers to sharing that data, but also an experimental framework that allows replication. And so I want to talk about what Autopilot does and sort of some examples of how we might do this experiment differently with Autopilot. Unfortunately, we don't have enough time to give an actual good description of what the system is, but in short, it's a distributed system for behavior that uses a lot of Raspberry Pis that are networked. And the basis of its design is that it's a bunch of modular components that you can sort of split out, modify, change, and use as you want to. It's a Python library for behavioral neuroscience. And so one thing that we can do initially just with the hardware, instead of needing to write a custom firmware and sort of writing our own new communication protocol, we just take existing code in the library. For example, we already have code in the library for controlling the GPIO input-output pins, and just extend that to make them behave in the sort of custom way that we want to. And but we keep all the functionality that the rest of the hardware objects has. This object already knows how to network to other things. This object already knows what it's like to make a pulse train, etc. So it makes it easier to extend, and it keeps it integrated with the system. And recent little feature I made, I've been working on recently is, if you don't like Autopilot, don't like the rest of it, but just want to use some of its hardware components, now you can just import them and use them anywhere. A lot of the backend stuff has been abstracted away. And then when we talk about a distributed topology, this experiment becomes a lot easier when you can sort of do it out of the box, where every object can be networked. Every LED can have networked messages sent to it to control its value, for example. So real-time closed loop control is the heart of the program. So in this case, we can, because it's relatively inexpensive to implement, and because it's possible to control a bunch of these things in parallel, we can scale our N and avoid a reproducibility crisis. And we can also scale the complexity. So an experiment like this becomes—
You have 2 minutes.
Okay, thank you. I wouldn't say relatively trivial, but easier than it was. And another thing we're excited about this distributed topology is we collaborated recently with the DeepLabCut folks and to work with DeepLabCut-Live. And in the paper, we talk about an experiment where we capture images on a Pi, send them to another GPU to process, and send the information back. So we think this is a promising foundation for many-to-many real-time image processing, many cameras, many GPUs, complex experiments. And this is part of a general transformation module that's easy to use, but I'm going to skip a little bit of that because I'm running out of time. And the final thing I have here on reproducibility is that because all of the components are integrated into the same system, the data can be unified at the time of its collection. So Autopilot keeps all of the data from all of your tasks. If you ever change the task, reassign an animal to a different task, it keeps track of that. Any parameters that change in your task, any version changes that happen to the code, any local changes you make to the code base, etc. We want to make sure every part of the experiment is documented so it's possible to reconstruct. And in addition to that, it comes with a single file, a portable task description, so anyone can re-implement your task exactly. So in sum, we built this tool to do the extravagantly complex experiments we all want to do. So for the future, a couple of things we want to do is, one, we want to integrate OpenEFIS acquisition. I think it'd be really fun to be able to acquire from 20 different head stages at once really trivially. That to me is really useful for example, social experiments. We want to have a better agent framework. So agents are just like what we call sort of like the different behaviors of a Raspberry Pi versus a GPU versus a computer in the swarm. So we want to do multi-timescale experiments where you have some observation in the home cage or something like that over the whole animal's life, but then are also able to integrate that with the day-to-day task that they do. Want to move to a task library so that we don't all have to rewrite the basis of a true alternative forced choice task every time and can build off of each other's expertise. Like someone else has a really beautiful graduated reward structure. I want to be able to borrow that. We want to work on our hardware library. Currently, we have this beautiful under construction web page, but what the idea is to be able to, because we're not prescribing any hardware components, as people make different components.
We need to, I apologize, but we need to wrap up.
Oh, gotcha. So then the final thing is we just need to make the code better. And then thank you everyone that was here. And these folks for helping me out. But I won't take any more time, thanks.
Okay, thank you so much, Jonny. I think it's a wonderful tool, and I'm sure a lot of behavioral neuroscientists will want to try it out, considering especially the increasing complexity of behavioral experiments. And so I'll encourage you to reach out to Jonny if you have any questions or you want to try it out. Unfortunately, we don't have any time for questions, but Jonny, you can quickly